Welcome to this Step 2 clinical knowledge review on biostatistics test-taking strategies. This video is brought to you by Roadmap to Residency. We are going to break down the most common biostatistics question patterns you will see on your board exam and teach you strategies to pick the right answer quickly and confidently. This is not a full biostatistics course. Instead, we are going to focus on the question types and test-taking strategies that will help you recognize the right answer on exam day. Make sure you have reviewed the biostatistics and epidemiology sections of your favorite review book and question bank before or alongside this video. Let us get started. Here is what we are going to cover today. First, we will learn how to recognize high-yield biostatistics question stems and study design patterns that the boards love to test. Second, we will apply test-taking strategies for sensitivity, specificity, predictive values, and likelihood ratios. These are some of the most commonly tested concepts. Third, we will master how to handle number needed to treat, number needed to harm, p-values, and confidence interval questions. Remember, review the biostatistics chapters in your favorite review resources for foundational content. This video is all about applying that knowledge strategically when you sit down for the exam. Our first strategy is study design recognition. When you see a biostatistics question, the very first thing you need to identify is what type of study they are describing. The boards will never say the words cohort study or case control in the STEM. Instead, they describe the study and expect you to identify it. For observational designs, if patients are followed over time without intervention, that is a cohort study. If patients with a disease are compared to patients without, looking back at exposures, that is case control. Cross-sectional looks at everything at one point in time. For interventional designs, random assignment to groups means randomized controlled trial, and a systematic review pooling multiple trials sits at the top of the evidence hierarchy. The boards love testing whether you can match the description to the correct design. Review the epidemiology sections of your study resources for the full breakdown of each study type. Strategy 2 is all about the 2x2 table. This is probably the single most tested concept in biostatistics on the boards. You need to know sensitivity and specificity cold. Sensitivity equals true positives divided by everyone who actually has the disease. The mnemonic is SNOUT, which stands for sensitivity rules out. A highly sensitive test, when negative, is excellent for ruling out disease. Specificity equals true negatives divided by everyone who does not have the disease. The mnemonic is SPIN, specificity rules in. A highly specific test, when positive, is excellent for ruling in disease. Now here is the critical board trap. Predictive values change with disease prevalence, but sensitivity and specificity stay the same. When the boards change the prevalence in a follow-up question, they want you to recognize that predictive values shift while sensitivity and specificity remain constant. Review the 2x2 table in your study resources until you can build one from memory. Now let us go through high-yield STEM recognition. For likelihood ratio questions, the STEM will ask how much a test result changes the probability of disease. The positive likelihood ratio equals sensitivity divided by 1 minus specificity. The higher the positive likelihood ratio, the more a positive test shifts your probability toward the diagnosis. For number needed to treat, the classic STEM gives you event rates in the treatment and control groups and asks how many patients need to be treated to prevent one bad outcome. The formula is 1 divided by the absolute risk reduction, which is the control event rate minus the treatment event rate. For number needed to harm, the STEM describes a side effect that happens more often with the drug. You calculate 1 divided by the absolute risk increase. Practice these calculations in your question bank until they are automatic. Let us work through our first practice question. A new screening test for a disease is evaluated against the gold standard. Of 500 patients with the disease confirmed by biopsy, the new test correctly identifies 450. Of 500 patients without the disease, the new test correctly identifies 400. The question asks for the specificity. Before we look at the answer choices, think about what specificity means and how you would set up the 2x2 table here. Take a moment to think through which number goes where in the table. Let us break this down step by step. Step 1. Build the 2x2 table. The 500 patients without the disease are your total negatives. 400 of them were correctly identified as negative, so those are your true negatives. The remaining 100 tested positive but do not have disease, making them false positives. Step 2. Apply the formula. Specificity equals true negatives divided by true negatives plus false positives. That is 400 divided by 500, which equals 80% or 0.8. Step 3, eliminate wrong answers. Choice C, 90%, is actually the sensitivity, not the specificity. This is the classic board trap, mixing up sensitivity and specificity. Choice D is a distractor. Choice B has no mathematical basis. The correct answer is A, 80%. The biggest mistake students make is calculating the wrong metric. Always reread what the question is actually asking for. Here is our second practice question. A randomized controlled trial compares a new drug to placebo for preventing strokes. After 5 years, 12% of patients in the placebo group experienced a stroke, compared to 8% in the drug group. The question asks for the number needed to treat to prevent one stroke. Think about what formula you need and what the absolute risk reduction would be before looking at the answer choices. Let us work through this answer. First, calculate the absolute risk reduction. The control group event rate is 12% and the treatment group event rate is 8%. 12 minus 8 equals 4%, or 0.04. Next, the number needed to treat equals 1 divided by the absolute risk reduction. 1 divided by 0.04 equals 25. This means you need to treat 25 patients with this drug to prevent one additional stroke over 5 years. The correct answer is C, 25. Choice A, 4, is the absolute risk reduction percentage itself, not the number needed to treat. That is a very common trap. Choice D, 100, comes from dividing incorrectly. Choice B, 12, is just the control event rate. Always show your work step by step in these calculation questions. Review the formulas in your study resources until they are second nature. Here is our third practice question. A study reports a relative risk of 0.75 with a 95% confidence interval from 0.60 to 0.95. The question asks for the correct interpretation. Think about what it means when a confidence interval for a relative risk does not cross 1, and what direction a relative risk below 1 indicates. Let us break down this answer. The confidence interval goes from 0.60 to 0.95. Since both numbers are below 1, the interval does not cross 1. For relative risk, this means the result is statistically significant. The relative risk of 0.75 means the treatment group had a 25% lower risk of heart attacks compared to placebo. Choice A is wrong because the relative risk value does not represent a probability of effectiveness. Choice C is wrong because a relative risk below 1 indicates a reduced risk, not an increased risk. Choice D is wrong because the result is significant, precisely because the interval does not cross 1. The correct answer is B. This pattern comes up all the time on the boards. Whenever you see a confidence interval for a relative risk, immediately check whether it crosses 1. Review the biostatistics sections of your study resources for more practice with these interpretations. Here is a critical test-taking pearl about statistical errors and power. A type 1 error, also called alpha, is a false positive. You rejected the null hypothesis when the null was actually true. A type 2 error, also called beta, is a false negative. You failed to reject the null hypothesis when the null was actually false, meaning there really was an effect, but you missed it. Power equals 1 minus beta, and it represents the probability of detecting a true effect when one exists. The most important thing the boards test is this. If a study concludes a drug works when it actually does not, that is a type 1 error. If a study concludes there is no effect when there actually is one, that is a type 2 error. And the best way to increase power is to increase the sample size. These concepts are tested frequently, and the questions are usually straightforward once you know the definitions. Review the hypothesis testing and study design sections of your resources for more examples. That wraps up our review of biostatistics test-taking strategies for Step 2 clinical knowledge. Let us recap the key takeaways. First, always identify the study design before answering the question. The boards describe the study and expect you to name it. Second, master the 2x2 table and know the difference between sensitivity, specificity, and predictive values, especially how prevalence affects predictive values, but not sensitivity or specificity. Third, for number needed to treat and number needed to harm, always start by calculating the absolute risk reduction or absolute risk increase. Then take 1 divided by that number. Fourth, for p-values, remember they represent the probability of data under the null hypothesis, not the probability the hypothesis is true. Fifth, for confidence intervals, check whether the interval crosses 1 for ratios or 0 for differences. Now go review the biostatistics chapters in your question bank and review books. Practice building 2x2 tables and running these calculations until they are automatic. Visit www.roadmap2residency.com for expert tutors and residency advisors who can help you with your board preparation. Like and subscribe for more high-yield board review content. Good luck on your exam, and we will see you in the next video.